So we're going to talk about wave behavior of electrons and particle behavior of electrons. And this gets back to that superposition idea where a quantum object can be two things at once. So back in 1924, de Broglie proposed that particles could have wave-like character in addition to their particle character. We observe the wave nature of an electron most clearly when we look at electron diffraction. So this is an example of electron diffraction. We have an electron source, and we have two slits. This looks very much like that double slit experiment that was done with light. And electrons go through here and interfere. They create an interference patterns just like waves do. So here the electrons are behaving like waves. If they behaved like particles, they would just go straight through and we'd see two bright lines where those particles went straight through. Because particles just traveling through space don't cause bending and diffraction and things like that. Only waves do that. So back to this part here, this is really kind of mind-blowing. That interference pattern is not caused by a pair of electrons. It's not caused by one electron wave coming through here and another electron wave coming through there, and then those interfering with each other. It's one electron wave going through both the slits and interfering with itself. So here the electron is definitely not a particle, it's a wave. So any questions about this? Mm-hmm.
So is it like where you like at collapse on one of the like when they don't collapse on one of the others, like part sometimes wave other times or is it both?
So yeah, when an electron isn't observed, it behaves like a, I think we have to assume that it behaves like a wave and a particle.
Mm-hmm.
But if you observe it, then it will behave like a wave or a particle.
Okay.
So in this diffraction experiment, we're observing the wave behavior, and so it's not acting as a particle. We'll see later where it does act like a particle.
If you observed it twice in the same experiment though, would it behave differently?
No,
No.
no, it wouldn't. Well, what I want to know is how does the electron know that we're looking at it? Obviously it doesn't, it's an inanimate object, but there's a lot of things I don't understand about this. So we can look at the wave nature of particles. This is an inherent property of individual electrons. And this is what's known as the de Broglie relation. The wavelength of this particle is inversely proportional to the velocity. So this is h, Planck's constant again, divided by mass times velocity. And down here, I typed out in these fonts the different, this is italicized V, that's non-italicized V, this is italicized nu, and non-italicized nu.
Oh my gosh.
Right? Yeah.
Whose idea was it to choose?
Whose idea was this? You should use a Greek letter that doesn't look like V. But they didn't ask me, so we had to deal with it. So one of the things that would help you is if you include your units and you choose the wrong thing, the units aren't going to work out. And so that would clue you in. We're not going to use this relation very much, but we'll do this example. What's the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond? Assume this length to be 1.2 times 10 to the minus 10 meters. So we've got 1.2 times 10 to the minus 10 meters, and it's saying that that's the wavelength. And it's asking what is the velocity. So we're going to use the de Broglie relation to calculate this. So the wavelength is equal to Planck's constant over mass times velocity. And Planck's constant was given on the previous slide, 6.624 times 10 to the, no, it's not 24, it's 26. Times 10 to the minus 10, 34 joule seconds. And now I'm going to go back and make sure. Yeah, 6.2626 times 10 to the minus 34 joule seconds. And then we've got the de Broglie relation. So that's H. And we're trying to find the velocity. And they told us what the wavelength is. So the wavelength is 1.2 times 10 to the minus 10 meters. And then we need one more thing. We need the mass. Hey Siri, what's the mass of an electron in kilograms?
Here's what I found from jetmione.com. The mass of electrons in kilograms is 9.1 times 10 to 31 kilograms.
So it's not 10 to 31. It's 10-31. She's reading it. It's 10 to the negative 31 kilograms. So Siri can be helpful, but sometimes a little confusing. I do not expect you to memorize Planck's constant or the mass of an electron.
But we always use that number?
H
No.
is always this number.
No, the mass one.
The mass of the electron? Well, if you're looking at the wavelength and velocity of an electron, you use the mass of an electron.
Okay.
But if you're looking at some other object, you use its mass.
But you will provide that?
Yeah. So we need to rearrange this equation. Good idea to cross multiply to get rid of the fractions. Well, that's not a good place to do that. Again, we're trying to get velocity by itself. So then we can divide by lambda m, divide this side by lambda m. So the velocity is Planck's constant divided by the wavelength times the mass. So we have 6.626 times 10 to the minus 34 joule seconds divided by 1.2 times 10 to the negative 10th meters and 9.11 times 10 to the minus 31 kilograms. If this question were on an exam, I am not going to try to trick you with the units. But we do have to use kilograms here because a joule is a kilogram meters squared per second squared. And so here we've got a joule times seconds. That cancels out one of the seconds. And then we're dividing by meters and kilograms. So the kilograms cancel and one of the meters cancels out. And so we end up with units of meter per second, which is a velocity unit. Hooray. Okay, 6.626 times 10 to the minus 34. Minus 10. That's what my calculator shows me. Thank you. Most calculators have a way that you can set them to display numbers. You just have to really yank it like you're angry. There you go. Most calculators have a way to set that they always display in scientific notation or always display in decimal notation. And there's also a way that if you get a number like this and you're like, I want to see that in scientific notation, there's a couple buttons you can press and it'll show it to you in scientific notation. So thinking about significant figures, the wavelength only has 2 sig figs, and so I want to stop this number here. Remember, if you're rounding anywhere that's larger than the ones place, you need to be really careful, and I highly recommend using scientific notation because we don't want to say that it's 61 meters per second, right? So I'm putting this into scientific notation. So I want to keep this place, but the next digit is 5 or greater, so this rounds up to a 1. And then this is times 10 to the something meters per second. So I'm going to be moving my decimal point after the first digit. 1, 2, 3, 4, 5, 6. So the exponent is 6. The question is it positive or negative?
Awesome.
It's positive. So if this was your paycheck, how would you feel about it?
Good.
I'd feel positive. Right? If it was $0.00034, I'd feel very negative about that, right? So that can help you remember what the sign is supposed to be on that exponent. Any questions?
Yes. I don't understand how you canceled out the stuff, the units.
How I canceled out the units?
Yeah.
I'm just going to get rid of that and do that again. So the units that we have up there are joules times second in the numerator and meters times kilograms in the denominator. And it looks like nothing's canceling out.
Yeah.
But we know from a previous slide that a joule is equal to a kilogram meter squared per second squared. So this is equal to kilogram meters squared per second squared times second divided by kilogram, meter times kilogram. So we have kilogram in the numerator and the denominator, those cancel out. I have meter squared in the numerator and meter in the bottom, so this meter cancels out 1 of the meters squared. And now what I've got left is meters times second divided by second squared, and the second cancels out 1 of those.
Thank you.
And that's not something that you need to know how to do. But that is why we have to use kilograms sometimes. Any other questions? So here's a question that doesn't involve any calculating. Since quantum mechanical theory is universal, it applies to all objects, regardless of size. Therefore, according to the de Broglie relation, a thrown baseball should also exhibit wave properties. Why don't we observe such properties at the ballpark? I've never seen a thrown baseball that looks like it's a wave. Have you? That'd be a cool pitch if you could figure out how to do that, right? So we've got 3 possibilities here. Because of the baseball's large mass, its de Broglie wavelength is minuscule and insignificant compared to the baseball's size. B, since baseballs do not have any charge, quantum mechanics does not apply to them. Or C, quantum mechanics does not apply to baseballs. This is one of those questions that just using some logic, you could get the right answer without really even knowing what this is. Because what does the first sentence say? Quantum mechanical theory is universal and it applies to all objects regardless of size. So, quantum mechanics does not apply to baseballs. Baseballs don't have any charge. Well, it says all objects. They don't have to have a charge. So that one's also wrong. So the first one is correct. And looking at the de Broglie relation, the wavelength is inversely proportional to the mass of the object. Now we were looking at the electron, and its wavelength was super tiny and its mass was super tiny, right? So if we're dividing by a really big number here, because baseballs would be measured in grams, then the wavelength is going to be very small, so small that you can't see it. There's a couple of questions on the worksheet that ask you to find, they're kind of ridiculous actually, but they ask you to find the wavelength of large objects. Yeah.
Is the V velocity or frequency?
That's a great question. In this equation, the V is velocity.
Okay. So does it like switch interchangeably depending on
Well, the problem is right here. V and nu in most type fonts, typefaces, you can't really distinguish between them. Right? So if you're looking at a non-italicized V versus nu, okay, both of the nus are kind of a little bit curvy. But when you italicize this font, you get this, and you're like, well, what? Yeah, so that's really could be very confusing.
So okay. Yeah.
But it's not something I'm going to try to trick you with. There are a set of things that I will try to trick you with, right? Like, you know, Celsius to Kelvin or Fahrenheit conversion, things like that, I'll try to trick you. But not this. The uncertainty principle. So if you try to observe the wave nature of the electron, then you can't observe its particle nature. If you try to observe its particle nature, you can't observe its wave nature. So the wave and particle nature of the electron are complementary properties. The more you know about one, the less you know about the other. So if we design an experiment that results in the detection of a single electron particle, like this is the same setup as the diffraction pattern one, except now there's a laser beam being shined across here, so that we can detect a particle electron and discover which slit did it go through. Because we can observe its particle nature here, we can't observe its wave nature. So I think if you turn this beam off, this would change to a diffraction pattern. You turn the beam on, you get that. Those electrons. How do they know? So Heisenberg came up with an equation. Delta x times m delta v is greater than or equal to h over 4 pi. So x here is the position of the electron. Delta x would be the uncertainty in the position. And delta v is the uncertainty in the velocity. And m is the mass. So the smaller the one uncertainty becomes, the larger the other has to be in order to remain greater than this constant number here. So you can know the velocity or position of an electron, but then, you can know the velocity of an electron, but then you can't know its speed. No, that was wrong too. Oh my goodness. I got V's and news swimming in my head. Okay, we're talking about position and velocity. Let's just use speed because velocity is problematic. Okay, the more you know about the position of the electron, the less you know about its speed. The more you know about its speed, the less you know about its position. Yeah?
Is that the same thing as saying they're proportional? Like, is the bigger one gets the smaller the other gets?
Well,
Inversely
no. They're not actually proportional because this is not an equal sign.
Oh, okay.
It's greater than this number. So they could both go up
Okay.
in theory. Yeah.
But this
Yeah.
one is greater than and all equal to, so it's possible they can be equal to?
Yeah, it's possible that it could be equal to h over 4 pi, but it's not guaranteed. It's just guaranteed that this is larger than this. And so delta x and delta v could both be very large, and this could be okay. Like personally right now, I have no clue about the position or the speed of any electrons, right? So that my uncertainty is huge. Well, it's bigger than h over 4 pi.
You know, nothing would be an infinite thing.
Yeah, I guess so. Right? But you can measure the speed of an electron, but then you can't know exactly where it is. You can measure exactly where an electron is at a particular point in time, but you can't know its speed that it was going. So, yeah, there's a lot of things just not right about quantum mechanics. So, which statement best summarizes the uncertainty principle? Both the position and the velocity can be accurately known at the same instant. Either the position or the velocity can be accurately known. Neither the position nor the velocity can be accurately known. So it's going to be B. We can know one or the other, but you can't know them both at the same time. In classical physics, particles move along paths, and they have velocity and position, and you can look at the forces acting upon them and predict what they're going to do. That's called determinacy. The present determines the future. Since we can't know the velocity and the position of an electron at the same time, we can't predict what path it's going to follow. So this is called indeterminacy. So the best we can do with electrons is predict the future statistically. We can say, well, there's this probability that the electron will be found within this region of space. Does that mean it will be in that region of space? No, it could be somewhere else. But maybe there's a 90%. So here we have determinacy. Batter hits the ball, goes up in the air, it's got a trajectory. It's got a velocity, there's a force of gravity on it, and wind could come into it as well. But a baseball player who has never taken calculus can do a very fine job of catching that ball, right? Without understanding classical physics. Because our brains do all that computing without us even realizing it. You learn how to catch a ball because your brain learns to predict how these things are going to affect the movement of the ball. It's really pretty amazing when you think about it. But that's not how electrons work. Here we've got a pitcher pitching a ball, and a good pitcher can pitch that ball exactly the same over and over again. If he was pitching baseballs, they would not go to the same place every time. So we would have a probability of, say, 20% that the electron baseball would be in this region, and 20% is in this smaller one, 40%, 70% within this region. Which means that one of them could come and hit this woman between the eyes, right? Now it's an electron. Would she notice? No, absolutely not. You can't say where a given electron is going to go. Isn't that disturbing? It's disturbing to me.